Thank you very much. Thanks for the invitation to speak. It's a great pleasure. I'm just going to send a link in the chat, which is just a link to the slides, because you will only be able to see the last 5 minutes or so at most of what I've said. So if you want to slip up and down, they're somewhat incomplete because I will be adding things as I go along, but I think it should be sufficient. Okay, yeah, sorry, this was just a bit of a joke. So okay, I think there's one more, and then okay, here we are. Okay, great, thank you. So this is joint work with Francesca Carocci, who's down in Lausanne, and this is something of an experimental talk. Because so really our motivation for doing this work comes from enumerative geometry, and more specifically it comes from something called logarithmic Gromov-Witten theory. But I realized when I was sort of thinking about this talk that actually most of what I'm actually going to talk about you don't really need to know anything about enumerative geometry in order for me to explain to you what I'm going to say. So yeah, okay, so I guess by us here, I don't mean like us, I guess I mean myself and Francesca, right? So our motivation is here. So I'm going to try and give this talk without really talking about enumerative geometry. I'll talk about it a little bit at some point. Those of you who are experts in enumerative geometry, I think you will already know sort of what I'm going for in this talk. So hopefully, we won't lose anything there. And we'll see, it's a bit of an experiment. It may be that somehow the motivation is important to appreciate the result, but I guess we'll find out. So okay, so that's just a kind of my disclaimer at the start, and now let's get going. So I'm going to be talking about tropical expansions, and tropical expansions we take no credit for. These are things that have been studied by many people over many years, and so I just wanted to spend a bit of time telling you what they are, at least from our point of view. And then I guess the new construction that I want to talk about is this sort of rubber torus action that we end up with. And it's just a very, I don't know, I think it's kind of a little acute sort of combinatorial description of a rather complicated group of symmetries, in some sense complicated. Okay, so let me get started now. So the first thing I have to do is tell you about toroidal embeddings. So our starting data here is always going to be the same. So it's always just a pair. Oops, daisy, sorry about that. So it's always a pair, so some variety, and some divisor D inside that variety, okay? And we say that this pair is a toroidal embedding if locally it looks like the pair of a toric variety relative to its toric boundary, okay? So this notion goes back actually to, I think, the first book on toric varieties, right? So Kempf, Knudsen, Mumford, and Saint-Donat, right? And that book was called Toroidal Embeddings. And you can find more or less this definition in that book. And it's been brought up and rehashed in various contexts in the intervening 50 years. So for me, maybe I could just explain this notation. So tau is going to be a rational polyhedral cone, and U tau is the associated affine toric variety. Okay, so relative its boundary. So let me just give a couple of examples. So the simplest example is a smooth pair. Okay, so X smooth and D smooth, and here, so what's going to happen? So locally, at least, so this is all local, right? So I'm just kind of lazy to pass to an open set, but I mean locally. So I choose some equation for D, okay, and that gives me some map to A1 such that the pre-image of 0 gives me D. Okay, so I'd like to say that X rel D is isomorphic to this pair A1 rel 0. Now, of course, that's not actually true because unless X is one-dimensional, and so instead we could just add in some kind of trivial factors, okay, locally, just choose some independent functions, and then we get some isomorphism of pairs, something like this, right? So relative to the hyperplane in the first factor. Those of you who are paying attention may have noticed that this is not a toric pair, okay, because the hyperplane isn't the toric boundary. And so the way that you kind of fix this, I mean, this is not, this is not supposed to be a deep point, is you just take, instead of taking n-1 copies, sort of dummy copies of the affine line, you take n-1 dummy copies of the torus, right? So the torus is the toric variety with no boundary. And now this really is an isomorphism of toric pairs. Okay, so this is the first example of a toroidal embedding. More generally, you can consider normal crossings divisors, right? So normal crossings means that locally, D looks like the intersection of some number of coordinate hyperplanes in affine space. And so we're going to end up with a situation, something like this. So I guess n is the dimension of X here, I guess. Okay, where the first R the map to AR is given by choosing functions for the D components of the divisor locally, okay? And then there's some n minus r sort of dummy functions that I just choose. Okay, so these are sort of, I guess, the most, for me at least, I guess these are the most important examples of toroidal embeddings, but there are others, right? So, what have I written down here? Basically, what I've written down here is the smooth affine toroid varieties, okay? But I could also allow, singular toroid varieties, and that's totally fine. So there's no real restriction. Of course, X will have to have normal singularities because it will locally be isomorphic to a toroid variety. But other than that, yeah, there's no big deal. So, okay, so these are the kinds of things we want to work with, and I'll give you some examples, why we might want to work this in a minute. I'll just have a little aside here. So this is not important, so you can stop listening for the next 3 minutes if you want. So if we just go back to this example of D being smooth. So, I wanted this to be isomorphic to a toric pair, which meant that I ended up choosing these sort of n-1, random functions, basically, or, independent functions, independent coordinates, I guess, near X. But somehow it doesn't seem that should be very important, right? So what we could do instead is just throw away these sort of redundant copies of GM, and we end up with a smooth morphism down to A1, whose central fiber gives me D, okay? So this is, we all know. And as we all know, right, this is only well-defined up to GM, okay? So it doesn't extend globally, right? Of course, unless O of D happens to be the trivial bundle. But globally, we do have something, right? So instead of taking A1, we can take A1 and take the quotient stack by GM, right? So we basically say, I'm going to throw away this indeterminacy, this GM worth of choices for the function defining D. And now this map does actually exist globally. Okay, in fact, I guess in some sense that's almost the definition of what A1 mod GM is, but also there's some sort of motivation coming from what I've been saying. And so here, now if you perform the base change to the origin in this sort of stack, you will get a copy of D. Okay. Why am I telling you this? So this is getting very, very close to the notion of something called a log scheme or a logarithmic structure. So, I guess as is always with online talks, I don't really know the background of everybody who's here, but I guess this is maybe for someone who has sat in talks about log structures and not necessarily understood what they are. Basically it means that you have something that looks like a toric variety modulo its dense torus, and then you have this map down to this is something that we would call it an Artin-fan, and this map is giving you some extra structure. It's basically giving you some functions, in this case the function defining D, and then you can build monomials out of those functions, and those monomials basically are the data of the log structure. And so what I'm discussing is, I guess, in a sense, it's a special case of log geometry. So a toroidal embedding is the same thing as a log scheme, which happens to be log smooth over the trivial log point. But anyway, so that was just a bit of an aside. That won't come up again. Okay, so anyway, so we have this pair which locally looks like a toric variety, but of course, this is just a local condition, right? So we have absolutely no control over the global geometry. So, for example, any smooth pair is a toroidal embedding, so pretty much anything could happen. It's just worth pointing out there's a lot of examples of, I guess this is sort of closer to my heart, of moduli spaces which are toroidal embeddings. So for example, Dilley-Mumford space has a normal crossings boundary. So that's an example of a toroidal embedding. The space of stable maps is, with some caveats, it is a toroidal embedding in some sense. And there are many more. Okay, so these are things that come up very often, and these kinds of structures are basically, I'm going to tell you something about the structure of these things, and that can apply to all of these cases. Okay, so we have no control over the global geometry, but that doesn't mean that we can't do anything. Okay, so in particular, there's an analog of the notion of a fan, okay, which is called the tropicalization, and I've put a little note here. So. So I'm going to define what I mean by tropicalization of a toroidal embedding, and I would like you to please forget about the correct definition, the non-Archimedean definition of tropicalization, at least for the next hour. They are related, but actually the relation is not as straightforward as you would somehow want it to be. Okay, so in particular, my X is not necessarily, I'm not giving it some embedding into a torus over some non-Archimedean field or anything like that. Okay, so please just. We're gonna do some operator overloading for this word during this talk. So what do I mean by the tropicalization? So for me, the tropicalization is an abstract cone complex, right? So what I mean by that is, what's the difference between a tropicalization and a fan? So a fan is a collection of cones, which, such that, when I intersect, I get a face of each and so on. So that it's a bunch of clones glued together along face morphisms. But also in a fan, that whole thing is living inside some ambient vector space, right? So I have the N lattice for my toric variety, and my fan is living in the vector space, the real vector space over that lattice. The difference with tropicalizations is it's basically the same thing. So I have a bunch of cones, I have a bunch of face morphisms, and I glue them together. But the difference is there's no ambient vector space where everything lives in. Okay, so each cone somehow has its own vector space. But when I move from sort of this cone to that cone, the vector spaces aren't necessarily the same. Okay, and we'll see examples of this in a minute. Okay, so it's an abstract cone complex, and it satisfies a sort of orbit cone correspondence. So the strata of this pair XD will be in correspondence with the cones of the tropicalization. Okay, so let me tell you how we build it. So locally, we cover our X by some open sets, and those open sets are isomorphic to affine toric varieties. So we get a bunch of cones, right, like rational polyhedral cones on those affine sets. And I'm going to take those cones, and I'm also going to remove these kind of redundant GM factors. Okay, so if you like, I just take a cone with its linear span rather than the cone with the kind of perhaps larger dimensional vector space in which it lives. And then we're going to glue these together. Okay, and somehow what I'm claiming here is that this makes sense. So if you have two open sets, then their intersection is going to look like some other toric variety, which is a face of the two cones. Okay, so I will show you how this is done on the next slide in an example. Yeah, so let's do a bunch of examples. So the simplest example is a smooth pair. Okay, so if I take a point, well, I guess if I take a neighborhood around D, then the toric variety I get is just A1, and the cone is just R positive, so I get some ray, and that's basically all that happens, right? If I'm away from D, then there's just no toric variety at all. It's just a big torus, and so I don't get anything. And so it's pretty boring. The tropicalization is just a ray. And I've sort of indicated how the cones in that tropicalization correspond to the strata. Okay, let's do a few more examples. So I think this example is sort of fairly self-explanatory, right? So I have this sort of intersection locus, which corresponds to the largest cone in tropicalization, and then the sort of components of the divisor, the smooth components D1 and D2, correspond to the rays. This example is perhaps a little bit more interesting. So I have two components of the divisor, but they're intersecting in 2 points, let's say. Okay, so they're intersecting in 2 points. And so the picture I get is, yeah, I mean, this is not a great picture, right? But I don't know if it's sort of clear what I mean, right? So there's two two-dimensional cones, which correspond to these codimension 2 strata. So in this picture here, that's sort of Z1 and Z2. And then they're glued together along both of their faces of their rays, right? So I have one ray here corresponding to D2, and then I have one ray corresponding to D1. So these two get identified. Okay, and this is maybe the first place you start to see that there's not really an ambient vector space in which this lives. Okay, because because I sort of perform this gluing, there's some picture like this, and it doesn't really make sense to talk about the ambient vector space in which this lives. And I guess one more example, fairly similar to the last one, is where you have, instead of two smooth components, you have a self-intersecting divisor, right? So now you have a single ray corresponding to that divisor component, and then you have a two-dimensional cone which is sort of glued to itself. So I guess the fundamental domain picture would be something like this. Okay, so this would both be corresponding to D. So are there any questions about that before I go on? Show the time. Okay, good. Okay, so this is some process. Let me just point out this process is definitely not reversible, right? So you're losing a huge amount of information when you do this. So there's no, there's no equivalence between toroidal embeddings and their tropicalizations like there is for toric varieties and their fans. Okay, so in particular, if D is normal crossings, right? So meaning that all our local toric models are like affine spaces. Then this is really nothing but the cone over the dual intersection complex of D, right? So maybe you can look back at the previous examples and sort of convince yourself of that fact. This is not true in general, right? So in general, this tropicalization is not just remembering the dual intersection it's not just remembering the intersection pattern of D, but it's also remembering something about the toric singularities that you have, so sort of local to each point of D. Okay, so we're losing lots of information when we pass this tropicalization, but nevertheless, it's still useful. Okay, and there's two constructions from toric geometry which generalize to this setting, which turn out to be tremendously helpful. So the first is subdivisions. Okay, so in toric geometry, if I give you a fan and I take some conical subdivision of that fan, then that corresponds to some sort of toric blow up. Okay, and something similar is happening here. So I can consider a conical subdivision of the tropicalization, and that's going to induce something that's called a toroidal blow up of of X, of the original pair. So one way to think about what these toroidal blowups are is that they're blowups in monomial ideals. Okay, so you might ask, what does monomial mean? Well, we have this divisor, and so local to every point, I have some set of functions or equations which are cutting out the components of that divisor. Okay, and a monomial is just going to be some monomial in those equations, basically. And of course, they exist globally as sections of line bundles. And so then I can assemble these into some ideals or ideal sheets, and those are going to be the things that give us toroidal blowups. So I'll just give you an example. It's a fairly simple example. We'll probably do some more complicated ones a bit later on. So I give you some pair like this. Okay, so this is a pair whose tropicalization looks like this, and now I'm gonna just take a subdivision of this tropicalization just by introducing a ray with slope 1, 1. Okay, so this is some subdivision of this thing up here, and it induces a blow up, and you can probably guess what it's going to be, right? So if this was toric geometry, I would be blowing up the stratum corresponding to this big cone here, which in this case is the intersection point of D1 and D2. Right, so this induces some blow up. Okay, I guess we're using green. So, so somehow this subdivision only really knew about the tropicalization, right? So again, I just sort of emphasize X and D and D1 and D2 could have been anything, as long as they had basically this tropicalization. I would get this subdivision, I would get some blow up. Okay, and so the way that you construct this, usually is to first do the sort of the toric blow up, right? So you have this local toric model, you perform the blow up there, and then you base change to X itself. So yeah, I mean, maybe, I don't know, maybe I can just say something slightly more than that. So locally I have some map from X to some toric variety, I don't know, I guess U tau, something like that. And then I have some blow up, and then I perform the base change. Okay, and this is going to be my toroidal blow up or my toroidal modification. Okay, so for toroidal embeddings, this map is an isomorphism, basically. So this thing is still a blow up. In general, for log schemes, this map doesn't have to be well behaved. In particular, it doesn't have to be flat, which means that this might not be a blow up. It could have positive dimensional fibers, but for us, it will always be an honest, birational modification. Okay, so we have some notion of toroidal embedding, and we have some notion of tropicalization, and we could try to study that. Okay, I seem to have lost something. Oh yeah, okay, this was another aside. So I said there were two things you could do with the tropicalization. So one is to do these subdivisions and then induce blowups. The other is to consider piecewise linear functions on the tropicalization. And again, as in the case of toric geometry, this gives you some Cartier divisors on X, some special class of Cartier divisors, which we call toroidal Cartier divisors. And this also turns out to be an important technique, but I won't need it so much today. But I just thought I would mention it. Okay, so we have this notion of tropicalization, and now I want to tell you a little bit about what an expansion is, okay? And this really goes back, I guess, to Mumford's work on something that we now call the Mumford degeneration. And it was then worked on by Nishino and Siebert, and there are many other people. I mean, I somehow couldn't really make this a complete list, but these have been thought about by many people. So I'll start with the toric setting. Okay, so the simplest example of a toroidal embedding is a toric variety, and then I'll sort of explain how it generalizes. So the idea is you have some toric variety and you want to degenerate it into a union of other toric varieties. Okay, and this is going to be something like the deformation to the normal cone, or some sort of vast generalization of that. So that here's the data that you start with. So I have my fan, let's say my favorite fan, the fan of P2, and then I take some polyhedral subdivision of the fan. Okay, so not a conical subdivision like we were doing in the previous part, but a polyhedral subdivision. So here's an example. And so let's call this P, for example. And what we can do is we can put P at height 1 in a lattice which is 1 dimension larger. Okay, so let's do that. And then I can take the cone over that thing. Okay, so I just basically draw all lines from the origin to points in P times 1, and then there's also something you have to do sort of asymptotically as your lines sort of approach to almost lie flat. And when you do this, you get a fan. Okay, it's a fan in this lattice, right? Meaning it gives me a toric variety of dimension 1 larger. Okay, now of course I can consider the projection from n plus z to z. And when I do that, you'll just notice that this cone maps onto the positive ray, the positive direction of z. And so what that means is that this toric variety that I'm defining, so this is the toric variety associated to this cone here. So I'm calling that X. It has a toric morphism to A1, okay, just given by this projection. Yeah. And this is going to be the degenerating family that we're after. So let me tell you what this morphism looks like. So remember, sorry, let me just sort of go back a little bit. So the input data was this P here, this polyhedral subdivision of the fan. So we have this toric morphism to A1. The general fiber is going to be basically X. Okay, this is actually a slight lie. In general, it's a sort of birational modification of X, but we always know exactly what it is, and it's always a toric variety. Just in many cases, it will just be X. The central fiber, on the other hand, is a union of toric varieties. Okay, and which toric varieties you get are sort of dictated by the polyhedral picture. So, oh yeah, okay, very good. So I already have the picture here. So this was where we started with, maybe I should use some colors. So we started with a fan of P2, and then we took this sort of polyhedral subdivision, like this. And so the way this works is you look at the vertices in the polyhedral picture. So here I'm going to call them V0 and V1. And each of those vertices gives me a toric variety just by zooming into the picture around that vertex, right? So if I zoom in close to here, I see the fan of, not P2, sorry, I see the fan of F1, right? So the blow up of P2 in a point. So let me try to draw the geometric picture. So, right, so this is F1, that's the blow up of P2 in a point. And over here, I see the fan of P2, okay? And you can see that they're joined together along this edge, which is corresponding to respectively the exceptional divisor in F1 and one of the 3 coordinate lines in P2. Okay, so there's some picture like this. So this is, of course, the degeneration to the normal cone of one of the torus fixed points in P2. And you can see how these two pictures, stack up quite nicely together. Okay.
Navid, question?
Yeah.
What assumptions are you making about X at the moment?
So at the moment, I'm assuming X. I suppose. So at the moment, I'm certainly assuming X is a toric variety.
But you're trying not to assume that it's complete or projective.
Yeah. Okay, that was your question. Yeah. So I probably might want to assume it's complete. Yeah.
Well, I mean, so my real question is maybe I didn't understand, because I was putting some extra assumptions in my head. I think I didn't understand your comment about the general fiber. So. Can you...
Oh, okay. I can actually just explain that, because I think I'm doing okay for time. So let me make a little extra page here. So let me do a slightly different example. So I will still start with the fan of P2, but now instead of considering this subdivision, I will consider this subdivision. Okay. Looks very similar. And now, there's something. Okay, so if I give you
I'm now okay.
You know this, right? Okay, maybe I'll explain for the benefit of everyone else though, since I started. So given this P, there's something called the asymptotic fan, which is basically what happens if I contract all finite edges, is one way to say it. Another way to say it is zoom out really, really far away and see what happens sort of asymptotically. So in this picture, that means that this red edge here gets contracted. Okay, so when that happens, you'll see that I end up with a picture like this. Okay, and of course you will notice this is not the fan that we started with, right? This is the blow up of that fan in a point. This is going to be the general fiber. Okay, so this is the general fiber of this family. Okay, so often it's not very hard to rig things so that the asymptotic fan is the fan that you started with, but in any case, at least I guess certainly as an enumerative geometer, we don't really care about passing to birational models of toric varieties. But in any case, that explains the slight lie that I told earlier. Okay, so this is the central fiber here. So you can see it's basically just obtained by gluing toric pictures locally together. We use this word expansion to refer to this. And one way to think about why we do this is as follows. So in this example, I'm going to call this central fiber Y. Okay, from now on. So that's what I'm going to mean by the central fiber. And there's actually a map from Y back down to the original toric variety I started with, which in this case is P2. So the way that works in this picture here is it collapses this entire, so this P2 corresponded to this vertex, it collapses that entire P2 onto the coordinate line that it was lying over, okay? And for F1, it just contracts the exceptional curve. So formally, the way that this is obtained is that, we had this fan, which was a fan inside n plus z, and we considered the projection to z, but we could also have considered the projection to n, right? And that would have given us a morphism, a toric morphism from x to x, okay? And then we just restrict that to the central fiber, and that gives us this collapsing now. And so somehow, I don't know, philosophically, what you should think is that you always have a sort of main component of this central fiber, which in this case is this F1 there, which is corresponding to the vertex of the origin in the original fan. And then you're bubbling off some additional components, which is somehow happening at infinity. Okay, so this is somehow the picture, and that's why we call it expansion, because you're expanding the target geometry that you're working with. Okay, are there questions, comments about that? How am I doing? Okay. Okie doke. Okay, so this is the story for toric varieties. Now I'm just going to claim that this extends straightforwardly to toroidal embeddings. Okay, so the input data is basically almost as it was before, so a polyhedral subdivision of the tropicalization. And now you can take the cone over it, and what you get is a conical subdivision of this product here. Okay, so you'll notice that there's no n anymore because the tropicalization is just a cone complex. It's not living in some vector space, but nevertheless, this product makes sense as a cone complex, and one can make sense of this cone as being some conical subdivision of that cone complex. Okay, so this thing is also a cone complex, and I'm going to call it upsilon. So this is some cone complex. And so let me, okay, there's going to be a little diagram here. Yeah, okay, very good. So what's going on here? So I've got my upsilon, which is this cone. This is a conical subdivision of this product, and then there's a projection map down to R. And I look at this composition here, right? So this diagonal map here. And one way that you can think about this is that if I choose a point on R positive, and I look at the fiber up in upsilon, then what I see is a polyhedral subdivision of the tropicalization. Okay, so somehow what this map is actually a family of polyhedral subdivisions. So maybe I'm doing better for the time than I thought, so I can actually explain things properly. So, so if we go back to the example that we had before, right? So I drew this. Polyhedral subdivision, and I probably something I didn't do, which I should have done, is actually tell you what point this new vertex is. Okay, so let's say this is the point 1, 1 in z squared. Then what this family is going to look like is I have my R positive here, and then I have sort of upsilon mapping down. And if I choose some point here, what's a good name for a real number? I don't know, x. Okay, so if I choose some point here, then what I'm going to see in the fiber inside upsilon is the polyhedral subdivision where this edge here has length x. Okay, so somehow the point in the base is parameterizing, or I guess if you prefer, this point has coordinates of x comma x. Okay, so this is sort of parameterizing this polyhedral subdivision. In this case, it's not a very interesting parameterization, it's just scaling of that length. But something you do notice is that when you set x to be 0, you recover the original fan, or in general, the asymptotic fan. Okay, so this is one way of seeing, this is probably the right way to see that the general fiber is going to be given by the asymptotic fan, because the general fiber in algebraic geometry should be somehow the special fiber in tropical geometry, and that's what we see here. Okay, so actually, I mean, that was actually in the toric case as well. But so anyway, if we come back now to this, whoops, what have I just done? Okay, I don't know what that is. Okay, so so if we come back to this picture here, okay. So the important thing to sort of focus on for the moment is this top row here. So we have a conical subdivision of this product. Okay, and the question is, how can we use that to get some geometry, right? So I've written a sequence of kind of fairly silly identifications here. So this product of cone complexes is a product of these two cone complexes. Okay, but a product of cone complexes is a product of tropicalizations is the tropicalization of the product. Okay, and I have to tell you what a product of pairs is. So this product of pairs is going to be this thing here, right? So I take, obviously I don't product the divisors, that wouldn't give me a divisor. So I take the divisor on one side times A1, and then I take, x times the divisor on the other side. Okay, but suffice it to say, this is the tropicalization of x times A1 with respect to some divisor. Okay. And therefore, since I have a subdivision of this thing, that gives me some birational modification of x times A1. Okay, so we get some geometric diagram. So this is the same diagram I just had of cone complexes now on the geometric side. Okay, so we have some birational modification of x times A1, and then we have this blue map down to A1. And again, just as before, the behavior of actually the general fiber and the central fiber is going to be dictated by this polyhedral subdivision P that we started with.
Just to interrupt you for a second. Mm-hmm. Are you assuming that the divisor is smooth in this case?
No. So any toroidal
construction is only local, right?
Sorry?
Isn't then the construction you're giving only local?
Oh, so you're worried about whether I should have a cone space rather than a cone complex?
No, I'm not worried about that. I'm sort of, I mean, I immediately see what the construction works locally if you have like a smooth component of your divisor, mm-hmm. But how do you ensure that this glues?
So okay. So I guess in one sense, okay. So in one sense, I guess I'm kind of lying in that. So for me, right? So okay. So I guess I haven't thought about this very hard, this particular issue, because we always want to think about the logarithm avoidance theory of these things, and then of course in that case you can always perform some initial blowups to resolve the singularities of your divisor components, and then you're talking about divisors with self-intersection, right? That's your
no, I'm not. I mean, I think I understand your construction just locally. I just don't know how to formally extend it.
So I think it does. So I mean, the way that I would, okay, I mean, we can maybe discuss afterwards. I think this does extend. I mean, I think the point is so maybe the easiest way to say it is as follows. So there is a canonical open cover of x times A1 where so for every cone in the tropicalization, I take the union of strata given by faces of that cone.
Maybe I think I know what I was confused about, actually. So you're really taking a polyhedral subdivision of the cone complex of X cross A1.
No, it's a conical, so it's a polyhedral subdivision of the cone complex of X, and then from that you get a conical subdivision of the complex of X times A1.
Okay. I think I understand. Yeah. But you don't get in general just I mean, it would always arise as a blow up of X cross A1 in the end.
Yeah, that's right. That's right.
Okay.
Yeah,
so in fact, if you're restricting to that, then okay, I see it. Okay.
Yeah,
great.
and in fact, I mean, to be honest, I'm mainly saying this as motivation. The way we actually set it up in the paper is that this is actually the data we start with.
Yeah.
So we don't actually start with P. We start with this data.
Yeah.
But I think actually, well, okay, maybe we can carefully work through.
Yeah. Anyway, sorry for interrupting. Thanks.
No. That's fine. That's fine. I mean, I think it is okay, but we can check afterwards. But yeah, in any case, we always start with this upsilon. And in fact, you'll see why a little bit later when we somehow go to the sort of correct context for this. Okay, so let me give you an example. So I'm going to have some divisor that looks like this. I've tried to draw it one dimension larger. I don't know if I've succeeded. So I have D1 and D2, and they just have some connected intersections. So again, the tropicalization I get is something like this. And I'm going to take this as my polyhedral subdivision. Okay, so there are 4 vertices here. So remember that the components, the irreducible components of the central fiber should correspond to the vertices. And now I'm no longer in the toric setting, right? So these aren't going to be, the components associated to these aren't going to be toric varieties, but there's also going to be relatively toric over the original geometry that I began with, okay? So here's what they are. So if we zoom in near V0, what it looks like is the tropicalization of X with this subdivision, this conical subdivision. And so that's what this toroidal blow up is, the blow up of D1 intersect D2 in X. Moving over to YV1, so this is some component that is living over this divisor D2, and what we're going to get is actually a P1 bundle over D2, okay? And then YV2 and YV3 will be, I mean, you can probably see this, P2 bundles and P1 times P1 bundles over this intersection, okay? And of course, when I say over here, I'm sort of, again, I'm implicitly using this fact that there is some sort of collapsing morphism from, so Y here is just the union of these, YVs, and there's some collapsing morphism which goes down to X. And when I restrict that to each of the components, this is what I see. Okay, so is that plausible to everybody? I mean, this is sort of somehow what would happen. Okay, and maybe a simpler example, maybe I should have done this example first, is if you just start with a smooth pair. Okay, so if you start with a smooth pair, the only polyhedral subdivisions you can really do are just sort of introducing additional vertices along that ray. And what you end up with is some central fiber that looks like this. So this is some iterated deformation to the normal cone of the divisor. Okay, so each of these, so maybe I should label these. So maybe this is V0, maybe this is V1, maybe this is V2. So I have YV0, YV1, and YV2 are the corresponding components. And each of these is some P1 bundle, and actually we know what it is. So it's the projective completion of the normal bundle. Okay, so this is something that is very well known to people working in Gromov-Witten theory, and I guess probably to other people as well. Okay, so let me just say a little bit about what happens in general. So I've given you a couple of examples. So, okay, how far do I want to go down? Let's go down to here. So it's certainly going to be true that the irreducible components of the central fiber are in a sort of bijective correspondence with the vertices of this subdivision. And the question simply is how to describe these components, okay? So, okay, yeah, I know I wanted to go further. Yeah, okay, so I wanted to keep this example in the bottom right in view. So each vertex has some associated cone sigma v, and that's a cone in the original tropicalization, and it's sort of the minimal cone which contains my vertex. So if we look at this example, for example, sigma v2 would be R2 positive, the positive quadrant, whereas, for example, sigma v1 would be R positive, just the vertical line would be sigma v1, it would be the line generated by D2. Right, so in my polyhedral subdivision, every vertex has some sort of minimal cone that it sits inside, okay? now there's, as we said before, that there's a natural map from YV down to X. And it just so happens that that actually factors through the stratum corresponding to sigma V. Okay, so sigma V is some cone in the tropicalization, so it corresponds to some stratum inside X, and I'm just going to call this XV or X sigma V. Okay, so again, if we look back in this example here, YV2 is mapping to the stratum corresponding to this two-dimensional cone, which is just D1 intersect D2, which is what we saw before. YV2 is a P2 bundle over D1 intersect V2. And similarly, for example, YV1 is mapping down onto D2, which is the stratum corresponding to this cone. Okay. Okay, so here's what we want to say. So we want to say that this map is a toric variety bundle, and moreover, that I can tell you what that toric variety is by looking at the local fan at V. Okay, so for example, we sort of saw that here. So if I look local to V, I see the fan of P2, and I notice that that lives inside this this lattice n sigma V. And so I want to say that this is a toric variety bundle with this P2 as its fiber. Okay. And in this example, that actually works. That's why I showed you this example, because it's somehow a nicer example. But in general, it turns out, unfortunately, life is not quite that easy. So this is true if I work over the interior of this stratum. So as long as I work away from the other strata, the deeper strata that it intersects, then this is true. Okay, so YV into XV is a toric variety bundle. But things can go wrong towards the boundary of XV. Okay, so let me just tell you a couple of things that can go wrong. So firstly, this morphism could just fail to be flat. Okay, so here's a stupid example. There are less stupid examples as well. But a stupid example is just I look at V0. Okay, so YV0 is just the blow up at D1 intersect D2 of X, and obviously that's not flat over X. Okay, there are by the way examples where the stratum is not all of X. I mean, okay, the example is basically take this example and then add a few dimensions to sort of make it exist. So this morphism can fail to be flat. Another thing that can happen is that this morphism can be flat, but it might not be a bundle. It might have certain fibers where the morphism is reducible, has multiple components. So here's an example of that. So if I look at V1 here, then this has a map down to D2, so the associated stratum in X is D2. And generically, this map is a P1 bundle, but over D1 intersect D2, there are two P1 fibers which correspond to these rays here in the picture. Okay, so there's a couple of things that can go wrong. But as I said, this is okay if I'm over the interior of XV. And so in particular, if this cone sigma V is maximal, right? So in other words, if XV is minimal, then this is perfectly fine and this works globally over XV, okay? And when I'm on the interior of XV, we have you can actually build YV from XV in a very explicit way. So there's some GIT construction. You basically do the toric GIT construction, but fiber-wise, okay? So there's a bunch of line bundles in the Picard group of the base, which are just, canonically given to you by the combinatorial data. And you can build YV as some kind of Cox GIT quotient, okay, by some appropriate GM. So we're writing. I mean, this is not the rubber torus thing I want to talk about. This is just something that came up in the process of this. I haven't been able to find this anywhere, so we decided to write it down. But if anyone knows, if this has been written down elsewhere, I'd be happy to hear. Okay, so now I can tell you about rubber tori, but maybe I'll pause for a minute and have a drink and see if there's any questions. Okay. So how far down do I want to go? Very good. So we're given some expansion. Okay, so Y is one of these reducible central fibers that we were just talking about, and this is this sort of collapsing morphism down to X. And the goal is to try to study automorphisms of this Y, which cover the identity on X. Okay, so that's the goal. We want to understand symmetries of this thing, and I will tell you why in a little bit. So the description turns out that sort of the upshot is there's some description which is purely combinatorial, it's purely tropical, and in particular, it doesn't really depend on the geometry of X. Okay, so if you have two X's with the same tropicalization, and then you look at the sort of the expansion given by some subdivision, then somehow the description you get in either case is going to be the same. I should say we're not going to, when I said this, maybe I should have said find some automorphisms. So we're certainly not claiming that these are all the automorphisms, but we are claiming that these are somehow the combinatorially, tropically most relevant ones. Okay. So, so let me motivate this a little bit. So I will talk about enumerative geometry. So, so in logarithmic enumerative geometry and logarithmic Gromov-Witten theory, what you want to do is you want to study curves in X which are tangent to a divisor. Okay, so here's a very nice picture of a curve C which intersects the divisor at a single point with sort of very high tangency. And there's a problem when you want to define a moduli space of such things. And in particular, you want that moduli space to be compact. Okay, and there's a problem, which is that somehow in the limit, you can get pictures like this, where your curve kind of breaks into two pieces, one of which is outside and one of which is inside the divisor. And in that case, it's a little bit less clear. In fact, it's much less clear whether, you know, which of these types of objects should be considered to be tangent to D and which shouldn't, because you want to add in enough things for your moduli space to be proper, but you don't want to add in too many things that your moduli space becomes, you know, well, you want to be able to understand the deformation theory of your moduli space, basically. So you don't want to add in too much. And so there's a solution to this, which, you know, goes back to, well, in algebraic geometry, it goes back to Jun Lee, but in fact, I think it, you know, is preceded by ideas in symplectic field theory, which is that if I look at this same family, what I should do in the limit is, instead of considering this non-transverse map to X, I should instead consider a transverse map, but to some expanded target. Okay, so what happens is my target bubbles off a P1 bundle, and this sort of squiggly curve, which was previously mapped entirely inside the divisor, is now mapping transversely. Okay, and this sort of infinity divisor, which is the strict transform of D under the degeneration of the target, is now functioning as the sort of, you know, the divisor that receives the tangency. Okay, so by the way, of course, this picture is an example of a tropical expansion. It's just the simple one associated to this polyhedral subdivision. Okay, so this is the picture in the case of a smooth divisor. And this is sort of well known in classical and has been around for about 20 years in Gromov-Witten theory. And there's something that's very well known about this, which is that if you have two maps which look like this, if they differ, so this YV1 is a P1 bundle over D, okay? And if you have two maps which differ by the C star action in the fibers of that P1 bundle, then you should identify them. You should consider those to be the same as objects of the moduli space, okay? And this is what's called the rubber action. And, you know, there's various ways of conceptualizing why you have to do this, but one basic reason is that if you don't, your moduli space won't be separated. You'll just have you'll have added in too many points, okay? So this was in the case of a smooth divisor, and this was sort of, you know, very well understood. And then the question is, what about SNC divisors? So can we firstly define some sort of theory where we expand the target for SNC divisors? And if we can, what is the correct notion of rubber action? When do we have to identify two maps two transverse maps to this expanded target? Okay, so this theory of logarithmic Gromov-Witten theory with expansions is due to, or was developed by Dhruv Ranganathan, and then recently, about a year later, in collaboration with Devesh Maulik. So there is a theory. I mean, okay, I should give people their dues. So there's a theory here where you don't expand the target, and that's what's called logarithmic Gromov-Witten theory. It's been developed by Abramovich and Chen, and Gross and Siebert. And this is a sort of alternative theory where you do expand the target, and, you know, depending on your application, one or the other theory is better. Basically, you know, it really depends on what you're trying to do. And so, in any case, this was really our motivation, which was so somehow in these papers there is a theory that's developed, but it's still unclear what the correct, what the sort of conceptual description of this identification should be. Okay, I can explain why it's unclear, maybe if people are interested, but there was somehow still something that somehow wasn't quite clear. So, okay, so let me tell you how we're going to go about this. So there's a simple observation which you make, which is that if I give you a polyhedral subdivision, there is an associated tropical moduli space corresponding to the edge lengths of that subdivision. So if we go back to this picture that I had here, as I've drawn it, so strictly speaking, what I've drawn is not quite a polyhedral subdivision because I haven't told you the coordinates of these points here. So what I've drawn is what's called a combinatorial type of a polyhedral subdivision, which is basically just the data of which cones these vertices have to be in and what the slopes of the edges have to be, but without specifying the edge length, right? So it's sort of like in tropical geometry, you have a graph and then tropical curve is like a graph plus edge lengths, right? So this is sort of the analog of a graph here. And so what are the edge lengths here? Well, let's say this is E1 and let's say this is E2. Then once these two are specified, the other ones are fixed, right? So this one has to also be E1 and this one has to be E1 plus E2. Otherwise, when I go in a circle, I won't get back to where I started with. Okay, so in this case, there is a moduli space. This really is a moduli space of edge lengths for this combinatorial type, and which is R2. Okay, so previously, in order to get our polyhedral subdivision, we had to choose some edge lengths, right? So I had to set E1 to be whatever, 2 and E2 to be 3 or something. Now we're going to just be a bit agnostic about that. We're going to fix some combinatorial type of polyhedral subdivision, and then we're just going to work relative to this base, to this moduli space, okay? And this was somehow the insight of this paper of Devesh and Drews, is that it's profitable to work over these higher dimensional bases. So let me say why am I saying higher dimensional base here? So remember previously we had upsilon mapping to R. Now we have upsilon mapping to R2, okay? And this is really a family of polyhedral subdivisions parameterized by these two edge lengths, okay? So it's a conical subdivision of this product and it's living now over a higher dimensional base, okay? So if I can draw the picture is something like this. So this is in black is the base and then in blue are the fibers, okay? So generically, if E1 and E2 are both non-zero, then I have some picture like this, where the lengths depend on what point I chose, right, in the interior downstairs. And then as I move off towards the boundary, as I move off towards the faces, things start collapsing, right? So for example, down here, as I move off towards the x-axis, what's happening is I'm setting E2 to be 0, right? So if we look in this kind of small picture here, it's a little bit small, E2 going to 0 gives me this picture down here, okay? And similarly, on the other side, when I set E1 to be 0, okay? So there's a family of polyhedral subdivisions over some higher dimensional base. And so what this informs is that we should have some new starting data, okay? So and this comes back slightly to the discussion with Martin earlier. So instead of starting with a polyhedral subdivision, we should instead start with a conical subdivision of this product, okay? Such that, satisfying some conditions, but one of the, in particular, what's going to happen is that this composition here is going to be a family of polyhedral subdivisions parameterized by points in the base. And the combinatorial type is going to be constant on the interior of any face, on the relative interior of any face of tau. But as I pass to smaller and smaller faces, the polyhedral subdivision will become simpler and simpler until eventually it collapses to just a sort of trivial picture. So this is our starting data, and this is what we might call, I should have said this, I guess this is a tropical expansion. Although I guess I'm also going to call the next thing a tropical expansion, so, okay. So just as before, this gives us some family, but of course now, previously we had a family over A1, now we have a family over this affine toric variety, right? So the toric variety associated to tau. And there's some conditions to ensure that this projection here is flat with reduced fibers, okay? And they turn out to be combinatorial conditions on this morphism of cone complexes, which one can write down very explicitly. This isn't due to us, this is due to, I guess, Abramovich and Karu, and perhaps even people before that. Okay, so why am I telling you all this? So we're getting to the description of this torus action that I've been kind of alluding to. So there's one more piece of information that I have to introduce, and this is somehow in my opinion, this is I think the key idea that just conceptualizes everything. So we have this tau, that's our moduli space of edge lengths, okay? So the points in tau correspond to choices of edge lengths. And for each vertex, we have some cone sigma where that vertex belongs. And there's a linear map between these cones, which just records the position of V in terms of the edge lengths, okay? So maybe it's just easiest to show in an example. So you can see, for example, that if the position of V2 depending on E1 and E2 is just E1 comma E1, right? So that's the position of that vertex. The position of V3 is E1 comma E1 plus E2, And then, the other ones are like this. I haven't written these as pairs because really these are belonging to each of these belongs to their own cone. Okay, so these guys have a 2-dimensional cone, whereas this only has a 1-dimensional cone, and this has a 0-dimensional cone. So there are these maps which just record the position of the vertex in terms of the edge lengths. And we're going to use these to define a torus action on this expanded target. So the tropical parameters, the edge lengths, coordinatize an intrinsic torus, which we just get by, I guess it's the dense torus inside this toric variety U tau that we're working over. Okay, and we call this the rubber torus. And then I guess the result, or the result is that there is, so if I have, so again, let's just sort of back up. So I have some tropical expansion living over some toric variety, and then there's a central fiber, which is the fiber over the torus fixed point, which we're calling y. Okay, and the behavior of y, y is like in these examples that we've seen before. And the statement is that there's a canonical action on this y, which covers the identity of x. And moreover, on each component, it's given by this tropical position map. Okay, so this tropical position map is a map from tau to sigma. And what we do is we just tensor by C star. And then the point is that there's an action of this sigma v on yv because, okay, at least in the case where this is a toric variety bundle, this is just acting as the dense torus of the fibers. Okay, we don't actually need the assumption that it's a toric variety bundle, but that's maybe the easiest case to think about. Okay, so for example, if we go back to this example here, what that looks like is that our torus is sort of GM squared with coordinates, I guess E1 and E2, and for instance, the E1 coordinate will act on this P2 bundle with weights, I guess, sort of 1, 1, right? So okay, sorry. So GM sort of E1 acts here with weights sort of 1, 1. That's because the tropical position map looks like this. And basically what that means is if I just draw the slope, 1, 1, it means it's the action on this P2 bundle which fixes this divisor pointwise, right? So it fixes that. It's the subtorus of the big torus which fixes that divisor pointwise, which is good because there's no action on YV naught here, right? So the actions have to, it's not just an action on each component, right? They also have to agree on the divisors where these components meet each other. And so on. And so somehow, I guess the thing to take away is that there is just this sort of tropically defined action on this expansion. And then I guess I'll just say for the enumerative geometers in the audience, this is the rubber action that you have to mod out by when you're considering expanded maps. Okay, so I have some, I have some map and I have to expand the target to make it transverse, and then you have to identify things if they differ by this action. And so I'll stop in a second, something new that you notice in this high rank situation. So maybe I can just go back up again. Sorry about this. So in the smooth divisor case, every component of the target has somehow its own torus, okay? And the torus is just acting on that component, right? So if I have a bunch of P1 bundles stacked on top of each other and I just have a C star action on each of those P1 bundles. In general, this is just not the case, okay? You have a single torus, which is acting on every component of the target simultaneously, and you simply cannot split it into individual tori acting on the components. So this is, this is clear. So for example, if you look at this divisor here joining two components, the torus action moves that divisor. It doesn't act trivially on that divisor, okay? And so there's just simply no way to split this into tori that only act on each component individually. And so you can imagine that this might be, a problem if you want to try and get a recursive description of the boundary. So this is somehow some of the geometry that comes out of this picture. But anyway, yeah, I think that was more or less what I wanted to say. So I'll probably stop there. Thank you.